So far we've discussed the strain tensor and the stress tensor and a little bit about vector notation, and then with respect to the stress and strain tensors, a little bit about the characteristics of each. In order to sort of press on towards developing the governing equations for a linear elastic material, we need to next talk about the equations of motion and equilibrium. So I want to start by just talking a little bit about the equations of motion in 1D to sort of get you acclimated to some of the concepts, and then we'll do the 3D case a little bit more formally and kind of making use of some of the notation and tensor features that we've discussed. Okay, so let's go and look at the equations of motion here. First, let's look in 1D. Okay, and the way we handle this in 1D is let's go ahead and consider. So here's let's say we have a long bar. Oops, and I'm gonna let the cross-sectional area here, just for the sake of argument, be constant, and I'm interested in some differential element that has length dx, and then this whole bar will have some cross-sectional area a. Okay, so if I can bring that little element outside. There's my element here that has cross-sectional area a, and this is width dx. If I look at the free body diagram that comes when I cut that, I have some force, and we'll say that's just f of x, coming off in the negative direction, and then on the positive direction I have some force, and this will be f of x plus dx. Okay, so I can write that that the sum of the forces, so this is a positive, this is a negative, that must be equal to the net force, which by Newton's second law must be equal to the acceleration, right? F equals ma is what we're looking for. So let's say the sum of the forces should be equal to ma. We're going to write m as rho times the volume, so this is density. And then a we'll just write as d squared u dt squared. That's the acceleration in terms of a displacement. Or we can write that as rho v u double dot. Okay, those are all equivalent. Okay, so let's go ahead and write that. The sum of the forces is going to be the positive direction. I have f of x plus dx. In the negative direction, I have f of x, and that's going to be equal to this quantity rho times the volume times u double dot. And the volume looks like just the cross-sectional area times dx, so it'll be rho a dx, so a dx being the volume, times u double dot. Okay, so I can then just go ahead and divide by the volume. So dividing by the volume, a dx gives me f of x plus dx minus f of x divided by a dx is going to be equal to rho u double dot. Okay, but we know that f over a is going to just be equal to the stress sigma, so we can write that sigma of x plus dx minus sigma of x divided by dx is equal to rho u double dot. Okay, now we just take the limit as the volume goes to 0, right, which is going to imply that dx goes to 0. What does this term here look like when dx goes to 0? Well, that just becomes a derivative term, and we're left with, I'm actually going to write it as a partial because there technically is a time component on here, and I'll write that then as partial sigma with respect to x is equal to rho u double dot, or we could write back in keeping consistency, rho squared u, sorry, del squared u del t squared. Okay, so this is the equations of motion. In this case, just a single equation. So the equation of motion in 1D. Now let's look in 3D, because sort of we're trying to develop a little bit more maturity in handling mechanics. So let's just say now in 3D, and I'm going to draw my continuum potato again. There it is. And it has its belt that lets you know it's a three-dimensional object. And there's basically two quantities. There'll be the volume, the internal volume, omega, and there'll be the boundary, gamma. Okay, so what do we want to say? We want to say that we're still going to use Newton's second law, F equals ma, but we want to say that there's two sources of force on this. So there's two sources for the net force. We're going to be a little bit more formal than we did with the 1D case. The first could just be the body forces. You know, they think of gravity or some magnetic force. And we are going to write that as the integral over the volume times the density times the body force, which is a vector term, and it exists it's a field quantity, times some differential volume d omega. We also potentially have surface tractions. Forces cannot come from anywhere else. And those are going to be written as something along the boundary of omega. And those will just be the traction, another quantity that varies on the boundary, times d gamma. Okay? So then the total force in the body is just the sum of those. And we can write the total force must be equal to the integral over the boundary of all the boundary tractions plus the integral over the volume of the body force. And let me just also mention that this is a body force. This is units. So this is a body force per unit mass. Okay? And let's go ahead. We're going to name this equation star. Okay? Now, by Newton's second law, we can write that F, and remember it's a function of t, and F is also a vector, must be the total acceleration times the mass. So this is going to be look just like our 1D case, rho times u double dot. Remember this is a field quantity, x and t, times some differential volume integrated over the volume. Okay, so that's the integral expression of Newton's second law. Call that equation double star. We can equate these now, so equating star and double star, we get that the integral over the volume of rho u double dot, and I should mention that u is a vector here also, u double dot of x and t d omega minus the integral over the volume of rho times b x and t d omega minus the integral over the boundary of the volume of t times x and t d gamma is equal to 0. So what do we see here? Well, hopefully you're probably looking at this going, this is not helpful. I don't know what we're doing with this. I have two integrals over the volume and then one over the boundary of that volume. So now we need to think about what could we do to that last term to make it an integral over the volume. So let's go ahead and consider the last term. And I'm going to write it in index notation for you because I think it's a little easier to handle there. And we'll write that then as integral over the boundary. This is going to be ti, and I'm going to drop that it's a function of x and t for the moment and just say integral over the boundary. Now this, we can say something now by the Cauchy stress formula. Hopefully you remember that from a couple lectures ago. Right? Ti is equal to sigma ij nj. So we could write this as the integral over the boundary of omega times sigma ij nj d gamma. Okay? We're almost where we need to be. Hopefully, now we have to reach into our toolbox from Calculus 3 and remember, how do we convert an integral that's written on the boundary into an integral that's written over the volume? And hopefully your answer is we use the divergence theorem. That's what we want to use here. So if you remember the divergence theorem, we can take an integral of this form where we have sigma dotted with n and write it as the partial of sigma now with respect to that same term integrated over the volume. So what that ends up looking like is the integral over omega now, not the boundary of omega, of the partial of sigma ij with respect to xj. And now instead of being over the boundary d gamma, it's over d omega. And then I often, in the shorthand that we've been using in this class, we would write that as sigma ij comma j d omega. So let's go ahead and substitute that back. And then we can rearrange to get that now everything is an integral over the volume. And we have rho u double dot I, I'm going to write everything now in index notation, minus rho bi minus sigma ij comma j d omega is equal to 0. We'll call that triple star for our equation. Okay, so what do we do from here? So we have to think a little bit about what this is saying. This equation, there was nothing specific about the body that we chose. So we actually could choose not only the body, but any subset of the body, and this equation, triple star, would hold true. What does that mean? That means that this equation holds true over an arbitrary volume. The only way that can work, given that it equals 0, is if the integrand itself is equal to 0. Okay, so let me write that down for you. Because triple star is true over any arbitrary domain in the body, then it's true if and only if the integrand is 0. So we can rearrange that to get the partial of sigma ij with respect to xi, or xj rather, plus rho bi is equal to rho ui double dot. Or we could write that similarly as sigma ij comma j plus rho bi is equal to rho ui double dot. Okay. Okay, these are the equations of motion. One of the things we should always do when we finish developing an equation like this is let's just check to make sure it makes sense to us. So maybe a good example could be we can compare this with the equations of motion from our 1D solution. So let's check versus the 1D solution. Okay, so if I just look up here and I only have one dimension, then xj just becomes x, and sigma ij just is sigma, and I can write that that's the partial of sigma with respect to x plus rho b is equal to rho u double dot. And if we don't have body forces, then b goes to 0. So if we have no body forces, then we end up with, let me back up. We end up with that the partial of sigma with respect to x is equal to rho u double dot, which is the exact same solution that we had as the 1D. Okay, so at least that checks out. Finally, we want to specialize this. So these are the equations of motion. We want to specialize this to equilibrium. So we have both the equations of motion and the equations of equilibrium. So the only thing that needs to change to make these the equations of equilibrium is that our acceleration term, the ma component of Newton's second law, is 0. So remember that in this equation, that term is just the rho u double dot. Okay, so we can write that to specialize to equilibrium, we just simply set the rho u double dot I term equal to 0 to get the following. Partial sigma ij partial xj plus rho bi is equal to 0. Okay? Or you could write that as sigma ij comma j plus rho bi is equal to 0. If you want to write that in direct notation, that looks like del, that's the gradient operator, dot sigma plus rho b is equal to 0. Okay, these are all equivalent. So these, I'll just circle this first one here for you. These are the equations of motion, or sorry, equations of equilibrium. Let's talk a little bit about what these equations are. I keep saying equations, but I just wrote a single term. So let me just remind you that these expressions, let me say not say these, this single expression represents 3 equations. Okay, let's count that. How do I know that? Well, the j is a repeated index, so that's just the sum. So the free index is just I. So there's one equation for I equals 1, one equation for I equals 2, one equation for I equals 3. So this represents 3 equations. How many unknowns? Well, for the above, the unknowns are going to be the 6 stress components. Right, sigma 1, 1, sigma 2, 2, sigma 3, 3, sigma 1, 2, sigma 1, 3, sigma 2, 3. So the question I want to pose to you, here's your question. How can we solve 3 equilibrium equations with 6 unknowns? Okay, so I mean, if people have forgotten everything about solving systems of equation. Usually they can recite that we can, if we have 3 equations, we can solve for 3 unknowns. If we have 6 unknowns, we need at least 6 equations. So obviously we can't just simply solve this directly. We need some more information to develop the governing equations for a linear elastic material. Okay, we get even further. In the case of the equations of motion, so in the case of the equations of motion, we have 9 unknowns for 3 equations. Right? Those include 6 stresses plus now 3 displacements, u. Okay, so I'd like you to think about that before you watch any of the next lectures, because we need to think about what are the pieces that we need to integrate this into a sort of a solvable system of equations that we can prescribe boundary conditions on and then extract the quantities we care about. And I think you know from your previous work in your engineering courses that we need to know stresses, strains, and displacements. So how can we link all those together?